Okay, hello everyone. Good afternoon. It's my great honor and for the first time to have this opportunity to present here. So, today I'm going to talk about my research on 3D damage evolution in silicon carbon fiber reinforced silicon carbon uh, composites at 1800 degrees Celsius, a quantitative study of pores and stream fields by in situ, micro CT, and DVC. My name is Zhang from Sichuan University. So let's get started. All right, so let me introduce my quickly go over what we're going to cover today. First, we'll talk about the research background. Next, we'll look at the experiment part, and then we'll see the post-treatment results and analysis. Finally, we'll wrap up with some conclusions. First, let me introduce this summaric matrix composites material. This composites is an advanced summaric matrix um, composite consisting of a silicon carbon matrix reinforced with silicon carbon fibers, offering a unique combination of properties, including excellent oxidation resistance, high temperature stability, uh, uh, and low density, and high strength. Uh, this superior, this superior properties make these composites promising candidates for aerospace applications, such as the chamber, combustion chamber, turbine outer casting, and guide vanes. However, the fabrication of these composites via process like CVI, PIP, and RMI inevitably introduce defects, including pores, cracks, inclusions, delamination, and fiber bond fractures at micron, even submicron scales. As you can see in this picture, the pores here vary in size. Some are large and some are small. These defects act as a critical initiation sites for damage evolution and are primary drivers for material failure. So that's why we needed to study them. Okay, moving on to the experiment part. So for the material preparation, we used CVI, which is chemical vapor infiltration, and RMI, which is reactive melt infiltration. We had silicon carbon fibers, and they were woven in 2D pattern, formed a 3D perform. Uh, Then we used a chemical vapor deposition furnace to coat the fiber with pyrolytic carbon at 1000 degrees Celsius. Then we deposit the silicon carbon matrix at the same temperature. This process may go through six to seven cycles until the density of the material increase to an appropriate range. After that, we did zirconium. After that, we did zirconium infiltration modification, um, and then we infiltration at 1900 degrees. Um, oh, and finally, we prepared the specimens by cutting and grading. Then we used the samples to carry out subsequent experiments. The experimental study was conducted under two distinct conditions: room temperature and high temperatures. That is 1,800 degrees. Um, here you can see that we performed CT scanning on this uh, specimens under different loading states. The two lines without fluctuations represent the specimens that were directly pulled apart to determine the maximum tensile force. Subsequently, the specimens that underwent CT scanning were imaged at the initial state. 30% of the maximum tensile force, 60% and 90% of the maximum tensile force. And after being pulled apart, then we found that the strength at high temperature is only half of that at room temperature. And the second, the maximum elongation at high temperature decreased from 1 millimeters at room temperature to 0.9 millimeter. Before to failure, the high temperature specimen underwent greater displacement under unit tensile load, absorbed more energy, and thus demonstrate an improved ductility. Okay, now let's look at the post-treatment results and analysis. So first, we use the high-resolution compute tomography, that is CT scanning, to obtain internal images of the material. Then we processed this image to extract defect information. We use image segmentation methods such as their shield segmentation and watershed segmentation, and deep learning techniques to assist in segmenting components that are not easy to separate, and then obtain different label image, which are the three-dimensional reconstructed images of each component. Thus, we are able to quantitatively characterize the characterize the distribution and the size of the defects. After we extracted and classified these defects, we found that the initial defects in these samples are mainly divided into these three types. First is the internal pores. The second is interbound pores. The third is micropores. Then by comparing and analyzing the key slice images at the different loading stages, we found that at room temperature, as shown in the left figure, no significant crack initiation was observed during the first three stages. In the first stage, a prominent lung crack become evident in the XZ cross-sectional slice. At high temperature, as shown in the right picture, small cracks already appeared in the second stage. And we can see the lacking of the material could also be observed. And therefore, next we conducted a layer-by-layer porosity analysis of the material in different directions under two temperatures. Figure A, B, and C is shows the condition at the room temperature. Figure D, E, and F shows the conditions at the high temperature. The height of the resulting peak is proportional to the porosity of the respective slice, while the peak-wise reflects the number of consecutive slices containing large defects. Thus, variation in peak height and width indicates the fluctuation in defects volume and their extent of directional propagation. Therefore, we found that the peak width of the curve, where at a room temperature or high temperature, basically did not change. Only the peak value changed. Only the peak value changed. So only next, we continued to count the changes in the number of pores in different size range at different stage under two temperature and their proportions in the total pore volume. Just as shown in the picture on the left, the results showed that the increase in porosity of this material, whether at room temperature or high temperature, is mainly caused by the rapid growth of small pores. However, the growth rate of both small or large pores is indeed faster at high temperature. In addition, the figure on the right shows the overall porosity of the two samples at different temperatures and different stages. We can also see that porosity growth rate at high temperature is significantly faster than that at room temperature. In addition, we also counted the porosity growth of different types of pores, that is, internal pores, interbounded pores, and macropores at a different loading stage under room temperature and high temperature, as well as their three-dimensional evolution images. This is a three-dimensional evolution image at room temperature. Basically, there are no significant change in either the appearance of the sample or the three types of pores inside it. But then here are the three-dimensional images of pore evolution under high temperature. It can be observed that the appearance of the sample shows obviously edge shrinks as well as the growth and aggregation of tiny pores in its appearance. By looking at the left pictures about the quantitative statistics of different pores under the two temperature, we can also understand the growth rate of different pores. It is obvious that growth of the three types of pores is relatively stable at room temperature, but the growth rate of the three types of pores under high temperature is all higher. Especially the growth rate of tiny pores is the highest. This also indicates that tiny pores are the types of pores most sensitive to high temperature. In the end, we used DVC, that is digital volume correlation, technology to calculate the 3D volume images at different stages under room temperature and high temperature, obtained a strain field that basically matches the final morphologic characteristics of the actual fracture. So here it can be seen from this slide that the results calculated by DVC basically correspond to the volume images of the fracture obtained by CT scanning. The DVC results at room temperature should multi-stream bands corresponding to the delamination fracture of the specimen. In contrast, the significant literal stream bands in the DVC results at high temperature correspond to the lacking phenomenon of the sample until fracture. At the same time, we also noticed some observations from the SEM images. For example, the fracture surface at room temperature is more uneven, while that at high temperature is relatively flat. When observing the fibers, it was found that the interface layer at room temperature is more prone to peeling in that circle. And the length of fiber pull out is longer. Under high temperature, the fibers that the interface layer are tightly bonded together, and the length of the pulled out fibers is also shorter. That is here. Finally, we have reached our conclusion section. The first is at the room temperature, failure is characterized by multiple cracking with delamination and extensive fiber pull out. In contrast, at a high temperature, the failure characteristic the local fracture denominate by a single primary crack, combined by pronounced leaking. The second is three-dimensional analysis reveals that high temperature is significantly accelerate damage initiation. The third is the DVC stream field measurements provide mechanical field evidence for the failure models. Okay, that's all my contents. Yeah. Thank you.